Hello everyone, here is a beautiful question of the rotational mechanics. There is a uniform disk having the mass small n and radius is capital R. So here is the center of the disk. This radius we consider as capital R and the mass of the disk we consider as M. The disk is pivoted at point P. Here the disk has been pivoted and it is free to rotate in the vertical plane. So if you consider this as a disk, it is pivoted at point P like this. This is point P where I am holding it, and this black part of the disk, can you see the black color on the sticker? This we consider as the center of the disk. Earlier the PC line, this is P point, this is C point, this is P point, this is C point. Earlier the PC line is horizontal, and this disk is free to rotate in vertical plane. Okay. Now question says it is released from this position. It is released from this position when PC line is horizontal, and then later on the center goes down here. Then the PC line will be making an angle theta with the initial horizontal line. At that moment, when this PC line is making angle theta, we have to find the angular acceleration of the disk. So this was the initial picture, initial position. Now we release the disk. When we release the disk from this position, this center goes down on a circular arc. So let's say the center comes down here at this location. Do you get this? The center comes here, and now that line makes an angle theta like this. Again, this distance is R. Okay. The gravitational force on the center of mass of the disk will be mg like this, and there will be some forces here at the hinge. I am not showing the forces at the hinge intentionally because we will be writing the torque about point P, which will be the moment of inertia about an axis passing through the point P multiplied with the angular acceleration alpha. Now, when we will be writing the torque of the forces which are acting at this hinge, which are acting at that point P, will be zero, because the forces are passing through the point P only. So the torque of the hinge forces will be zero. That's why I am not showing those forces in the free body diagram. Now for mg, if we extend this line and we draw a perpendicular, this is R, this angle is 90 degree. So the perpendicular length here I am showing should be equal to R cos theta. This distance was R, this angle is theta, so this perpendicular distance will be R cos theta. About point P, there is torque of only one force, that is the gravitational force, and due to that gravitational force, the disk is going down like this. So the torque about point P can be written as R cos theta mg. Now we need the moment of inertia of the disk about an axis passing through point P like this. We know the moment of inertia of the disk about an axis passing through its center of mass. What is that? Speak up. Correct. mr square by 2. Let's do that here. Suppose this is a disk. For the disk, the moment of inertia about an axis passing through its center of mass is mr square by 2. We need the moment of inertia about this axis passing through point P and perpendicular to the plane of the disk. To obtain the IP, we can use the parallel axis theorem. IP is equal to I center of mass plus m into distance square. I center of mass is mr square by 2 plus m into the perpendicular distance between these two parallel axes is R. So mr square by 2 plus mr square. This is the moment of inertia. which is 3 by 2 mr square. It means here IQ becomes 3 by 2 mr square. See whether the disk has this position, axis here and axis passing through center. Perpendicular distance between them is r. Whether the disk has this position, axis here and axis passing through here, the perpendicular distance between them will remain r. I hope you get it what I mean to say. Let's say earlier the disk was like this. Now later on the position of this disk gets little bit changed. I am orienting the disk, let's say after some time about this hinge point. Here are the two positions. I'll show them with a different color for sake of clarity. Now for this new position also, if we check, this is the center of the disk and here this distance will be again r only. So the moment of inertia about this center is mr square by 2 and we can find the moment of inertia about this. Okay. Alpha is our target, the angular acceleration. Here we can cancel out that m, here we can cancel out 1r from the computation. So alpha comes out to be 2g cos theta divided by 3r. Any option matches with this? 2g cos theta divided by 3r matches with the first option. So correct answer for this question will be the first option. I hope you enjoyed this solution. If you have any doubt in physics, you can post that in the comment box. We will discuss them. If you enjoyed it, please like this video, share it with your friends and kindly subscribe to this channel. Stay awesome and thank you.